Hello and welcome to Physical Attraction. This episode on nuclear physics is about the liquid drop model and the semi-empirical mass formula. Sounds exciting, and we're going to get right into it. There's a famous saying that's attributed to the statistician Henry L. Box, but it's one of the most important sayings for thinking about physics and science in general, the process of how scientific theories and scientific models work. He said, "All models are wrong, but some models are useful." What does this mean? Well, a model is a simpler representation of a more complex system. Maybe you're simplifying it because you suspect in advance that it's going to be safe to ignore certain physical processes that are really going on. Perhaps you know in advance, for example, that something is going to be very small compared to what you're interested in. For example, photons from the sun actually exert a tiny pressure on everything they hit. If you're designing a lightweight probe that's going to head towards the sun, you're going to need to worry about this photon pressure and how it will impact the probe. But if you're designing a bridge, you don't need to be concerned about the difference in pressure due to radiation during the day and night, because the weight of the cars driving over the bridge will be more important. Other times you need to use a model because things are unknowable or irrelevant. Take a classic example from thermodynamics. We're talking about atoms and molecules colliding with each other and with surfaces. Now let's say you want to figure out how all of these atoms striking you will make a difference to you. Now technically speaking, to give a full accounting of all the momentum transfer that's going on, of every collision, you'd need to know the precise location and speed of every atom at all times. But when you have 10 to the 23 atoms, billions upon trillions upon billions, this becomes impossible to measure or know. But luckily for us, we only care about what happens on average. After all, when you're underwater, or under the atmosphere, you don't feel pressure as many individual atoms bouncing off you, but instead you feel the time-averaged force. You can replace a detailed accounting of individual atoms with statistical mechanics, thermodynamics, and statistical averages. These things are models where we treat idealised heat engines or big thermal baths of temperature. The information is incomplete, and so in some ways it's wrong to pretend that the pressure pushing down on you is uniform and not actually made up of many tiny atomic bumps that take place over many different seconds in many different locations. But for most of your purposes, it will be good enough to do that. Maybe you know the laws of physics that apply, but actually performing the explicit calculation would take far too long without a noticeable difference in the result. A classic example of this is climate models, which divide the world and the atmosphere up into lots of little grid boxes. Then, for each box, temperature, pressure, precipitation, whatever, is calculated based on the known laws of physics and the influences from surrounding boxes. Processes that take place in areas smaller than a grid box, such as the formation and precise dynamics of clouds, are often not in the model directly, but through parameterizations where we represent the complex process of cloud formation by its average effect, we can hopefully ensure that we don't go too far wrong. It might take far too much computational effort to accurately simulate what the clouds are doing, but it's better to put in a parameter that says perhaps this area is cloudy 10% of the time or 20% of the time for the purposes of the radiative field in a simple model. And still other times it's because you don't actually understand the physical processes that underlie what you're trying to model, observe, and explain. In this case, you might come up with what's called an empirical rule, something based on observations. You don't have any explanation for how it works. You don't quite know why this rule seems to fit the data very well, but it certainly does seem to fit. Maybe what you've done is stumbled across an approximate version of a deeper understanding, or one that holds pretty well in the regions that you're interested in. Take for example gravity. The ancient Greeks used to think that the natural trajectory of a ball, if you threw it, was a parabola, a curve that bends downwards and arcs downwards. We now know that there are several forces acting, gravity, air resistance, that determine the shape, and without these forces the ball would carry on moving in a straight line at the same speed forever. So the model that throwing a ball outwards will result in it arcing down in a parabola, that's wrong. That's not true, that's not based on any reality, it's not based on any understanding of the physical laws. But even though it's wrong, it still gives you a better prediction than someone who told you it would fall straight down to the floor like in a cartoon or fly off forever. There's no understanding of the underlying physics, but it does give correct predictions. So it's another example of a model that's wrong but useful. Or how about Kepler's laws of planetary motion? Actually, a lot of credit for those should go to Dutch astronomer Tycho Brahe, who spent years in meticulous detail recording the motions of the planets through his telescopes. He also lost most of his nose in a duel that started from an argument at a wedding party, and people have been continually digging up his grave to learn more about the prosthetic brass nose that he wore. I'm not saying that losing your nose means that you necessarily have more free time to devote to astronomy, it's just an interesting historical fact. From Bray's observations, Kepler figured out all kinds of laws of planetary motion. For example, the fact that the square of the time period of a planetary orbit of the Sun was proportional to the cube of the semi-major axis of its elliptical orbit, which is basically the long dimension in an ellipse. But he didn't know why those rules fit the data so well. It would take Newton's laws of gravity to actually explain them. And a similar thing happened to Hubble centuries later, when he noticed that galaxies seemed to be speeding away from us at speeds proportional to their distance. Again, at the time, there was no theoretical explanation for this, but even though we didn't understand the underlying laws of physics, you could use it to make estimates and predictions, and so it became a part of physics. These models are all wrong in some way. There are special cases when they fail, or they actually seem to work and give you the right answer, even though the reasoning behind them is totally wrong, or they're mostly correct, and based on physics that is almost always accurate except in some special cases, but there's still technically not the full truth of what's going on, and in many ways we still haven't uncovered the full truth of what is going on, the ultimate laws of physics from which everything can be derived if they even exist. In a sense, this is true of physics itself. Our understanding is still incomplete, and the calculations we make could be based on a totally incorrect understanding. Newton's version of gravity, for example, doesn't posit the idea that it's caused by curvature in space and time, like general relativity does. But you can still use it to make good calculations. You can get rockets to the moon with Newton's laws. So what we deal with in physics is successive approximations to reality. And sometimes when you have a good model, but you don't understand why it works, the best thing you can do is to throw up your hands, admit that you don't understand why it works, but that it does work, and then, quote-unquote, shut up and calculate. This was the dilemma facing physicists when the nucleus was first discovered. As soon as it was realised with the work of Rutherford, Meitner, Chadwick and others that the nucleus of an atom was made up of even smaller particles, and that some of them were charged protons, they knew that there must be some incredibly strong force holding the nuclei together. For a while, scientists thought that maybe the nucleus was held together by a kind of glue of electrons, negative charges that stopped the protons from flying apart. But this model couldn't explain the size or stability of the nucleus either, let alone its charge. Let's put this into numbers. The radius of the nucleus is measured in femtometers, that's 10 to the minus 15 meters, a millionth of a billionth of a meter. Atomic scales are 10 to the minus 10 meters, so the nucleus length scale is 100,000 times smaller than the atom. But volume is the cube of length, so the nucleus is a million billion times smaller in volume than the atom. These protons then are packed in very tightly. The charge on the proton is the same as the charge on the electron. If you apply Coulomb's law of electromagnetic force, which is good enough, you see that two protons separated by 10 to the minus 15 meters should repel each other with a force of around 230 newtons. Now, on the scales we're talking about, that's a truly astonishing force. The force due to the weight of an object is roughly 10 times its mass, so that's like having a 23 kilogram object pressing down on a single proton, which weighs 10 to the minus 27 kilograms, or 1,000 trillion trillionth of a kilogram. The force of gravity between the protons is absolutely pathetic by comparison, and makes no contribution to the energy balance in the nucleus that we can really measure. So you need a new and astonishingly powerful force. But this just raised more questions for the physicists at the time. The forces that were described in detail at the moment were electromagnetism and gravity, and for the most part, in the classical limit of stuff that humans deal with every day, they can be described by inverse square laws. That means that you basically have an equation that says the magnitude of the force between two particles is proportional to the product of charges, or masses, divided by the square of the distance between them. So, it's a simple case of the bigger something is, the more it will attract other things. The larger charge it has, the more electromagnetic forces will be involved with it, and this force falls off pretty quickly as you go away from the object. But classically at least, the force fields extend throughout all of space and time. You and I attract each other, you're attracted to Jupiter and your pencil case, and any other object in the world, but the relative size of the force means that you don't notice most of these tiny little pulls. And these laws are remarkably mathematically similar. The only real differences are that gravity is far, far weaker because it has a much smaller constant of proportionality out the front, and gravity is only attractive. There's no such thing as negative mass that repels, gravitationally speaking. At least as far as we know. But the strong force is clearly different. It doesn't fit this nice pattern of inverse square law behaviour. If it did,
then you have to answer the question of what stops all the nuclei from just merging with each other. You'd have this very powerful, strong force that's enough to overcome electromagnetism, and it would eventually just pull lots of nuclei together, creating a huge nucleus ball. Such objects would exist, and we'd see them if the strong force was so powerful. Instead, though, the nuclei behave very strangely, and the more nuclei that were discovered, the more strangely they seem to behave. If the strong force truly is dominant, and obeys similar rules to the other forces, heavier nuclei should be more stable, right? Because they have more glue from the strong force and the gluons that keep the thing together. But it turns out, of course, that they're not. The heaviest elements are radioactive and spontaneously decayed into lighter elements, and adding in more nucleons didn't make the situation any more stable. We now know that this is because the strong nuclear force doesn't obey a simple inverse square law. Instead, it's repulsive at very tiny distances, which keeps nuclei from becoming too compressed together, and attractive at longer distances, but only for about the range of a medium-sized nucleus. After that, the attraction rapidly drops off, much faster than inverse square law, becoming very small at only very short distances away. So it's as if this force just exists to bind the nucleus together, without appearing in too many other contexts. It's almost perfect for keeping certain types of nuclei together, pushing certain kinds of nuclei apart, and making sure that you can't have a nucleus that's just too strongly compressed, or indeed too broadly spread out. Understanding the precise nature of the strong force, this mysterious force that seems to do precisely what it should for nuclei to exist, turns out to be incredibly difficult. There's a whole theory, quantum chromodynamics, that explains how the quarks, which make up the protons and the neutrons, interact with each other to produce this strong force between protons and neutrons. It took until the 1970s for theoretical understanding of the strong force to significantly advance. So the physicists of Rutherford's era in the early 1900s were many breakthroughs away from any hope of a theoretical understanding of the strong force, and hence what's really holding a nucleus together. But the fact that they couldn't do proper calculations with a full theory of the strong force didn't mean that they couldn't come up with a model that might help explain why some nuclei were stable and others weren't. They could see that this was clearly what was going on with the strong force, that it seemed to be repulsive at short distances, preventing nuclei from collapsing in on themselves, but attractive at long enough distances to keep the nucleus together, but also not so attractive that it would be able to pull in nuclei from surrounding nucleons or anything like that. And this was no idle question either, because as we talked about in the last episode, Rutherford had proposed that the stars were powered by the fusion of light nuclei, and Lise-Meitner would later prove that if you bombarded certain unstable nuclei with neutrons, you could make them split apart and release energy. The question of whether a nucleus is stable or not is really all about energy. Broadly speaking, and this is very broad, when physical systems are free to change, they usually like to settle in the state with the lowest possible energy. We always imagine a ball rolling into a ravine, into a ditch of lowest potential energy. The most stable place for the ball to be is right at the bottom of the ditch. It has the lowest amount of gravitational potential energy, and you have to put in the most energy to shift it back up the hill. This is all related to things like the second law of thermodynamics, where entropy and disorder tend to increase, and processes cause energy to be lost at waste heat that dissipates into the universe. This kind of thing tends to mean that systems generally settle into states of lower energy. It's not always true, but they generally do. It turns out that a similar logic applies to nuclei. Stable nuclei are the ones with the maximum in binding energy. Now, this can be a little confusing. The binding energy essentially measures how much energy you'd have to put into the nucleus to tear it apart completely. It's the amount of energy that would be released if the nucleus somehow formed from a bunch of protons and neutrons joining together. So you can think of it as a kind of negative energy that is held in the bonds between the protons and neutrons due to the strong force. Now, the higher the binding energy, the more stable the nucleus. And this makes sense really, because high binding energy means you need to put in a lot of energy to tear the nucleus apart. A low binding energy means that the nucleus isn't that tightly bound, and the amount of energy that is required to pull it apart, or that would be released by allowing them to come together, is smaller. So this is why both fusion, joining nuclei together, and fission, splitting them, can release energy. It all depends on the changes in binding energy due to the process. So when helium nuclei fuse together, the result has more binding energy, so energy is released. When a uranium nucleus splits apart, the resultant products are more tightly bound together, so energy is released. Then the question becomes, can we work out a formula for the binding energy of a particular nucleus? Then, not only would we know how stable nuclei are, but we'd also be able to calculate how much energy nuclear reactions should release, or what might require them to happen. After all, if you had this formula that could work out the binding energy of different nuclei, you just need to figure out the binding energy before and after and subtract them. Whatever the difference is must be released. And this would show you what kind of nuclear reactions would require energy to take place, and what kind of nuclear reactions might take place on their own, and how much energy they might release. But of course we don't have this closed, nice theoretical model of the strong force yet. But even if you don't fully understand the strong force and quantum mechanics, as they didn't at the time, can you do this just based on studying different nuclei and different nuclear reactions? Can you do it based on a model that's wrong but useful? Well, the answer to both of these questions is yes, and that's the topic of today's show. The formula that was used for decades to calculate binding energies, and is still used a lot today, is called the Semi-Empirical mass formula. Now, semi-empirical means that part of the formula is based on a model of the nucleus, while part of the formula is based on observations and experiments that tell us about how the nucleus really is. So this is the empirical part. You can derive empirical laws just by looking at how things behave in reality. So, for example, if you were throwing projectiles out, you might notice that they all arc downwards in parabola, and you might even be able to figure out a relationship between the speed at which you launch the ball and, how far away it comes to rest. That's not based on an underlying theory. You don't understand the kinematics there. You haven't worked out how the forces are acting on the ball, how its acceleration and velocity over time are changing, that kind of thing. But you have come up with an empirical formula that links a variable you know, which is the speed at which you're launching the ball, and how far away it eventually goes. So with no understanding of underlying physics and just a lot of observations, you can still figure out mathematical relationships that have some of the underlying physics embodied in them. And that's what they did with the nucleus in the early 20th century. So it's at times like this where I really wish that I had a blackboard for this show, and maybe this sort of thing is better done on YouTube. I'll have to see what you say in the comments. But I don't, so I'll put the formula in the show notes if you want to gaze at it, and just describe what each term is so that you can get an idea of how it works. Then, armed with our now vague understanding of the nucleus, we can talk about fission and fusion in later episodes. The semi-empirical mass formula is so useful because it can tell you the approximate binding energy of a nucleus just based on two numbers. The number of protons, Z, which tells you the charge, and the total number of nucleons, A. So the semi-empirical mass formula starts off with what's called the liquid drop model. The idea here is that we don't really understand the nature of the strong force well enough to calculate things explicitly, but we do know some things. We know that each nucleon takes up the same volume, roughly. We can get a decent idea by imagining a droplet of water. Such a droplet is made of many tiny molecules, in the same way as the nucleus is made of many tiny nucleons, protons and neutrons. Now, each nucleon attracts other nucleons. We know that every one of those interactions will contribute to the binding energy. To understand this, imagine you're being held in place by many little strings. Breaking each string requires a little more energy, and the total you'd need to put in would be proportional to the number of strings holding you down. But we also know that the range of interaction must be limited, or else all the nucleons would clump together, and superlarge nuclei would not only be possible, but more stable than the light ones. That means that elements like hydrogen and helium probably just wouldn't exist in the same abundances as they do today. So to first approximation, why not just assume that each nucleon only interacts with its nearest neighbours? That gives us as many interactions as there are nucleons. So, given that each interaction is like a string tying you down, and each of those has its own little contribution of energy, we get a contribution to the binding energy that's proportional to the number of nucleons we have. This is called the volume term. Since each nucleon takes the same volume, the total volume is also proportional to A, which is the number of nucleons in the nucleus. The radius of the nucleus is proportional to A to the power of 1/3 in this model, in the same way as you would have a sphere, for example, made up of lots of little spheres. But of course here we've made a slight mistake, because not every nucleon has the same number of nearest neighbours. If you're in the middle of the nucleus, you might be touching other nucleons on all sides. But if you're on the edge, you have fewer neighbours than nuclei in the middle. This is because part of you is just touching empty space, so you're being held down by fewer interactions. So this is corrected with a surface term, which compensates for the nucleons that have fewer nearest neighbours. And we can say that, well, this will be proportional to the surface area of the nucleus. That'll tell us about how many nuclei are on the outside. So for example, the surface term might be quite big for a small nucleus like helium, where all of the 4 nucleons are sort of touching empty space and only interacting with maybe 1 or 2 nearest neighbours. But the surface term would be much smaller compared to the volume term for a big nucleus like uranium, which has 90 little nucleons floating around. There'll only be a small fraction of those that are actually on the outside surface, and there'll be lots in the middle that have as many nearest neighbours as you like. So since we know that each nucleus seems to take up roughly the same amount of space, this compensating surface term is proportional to a to the power of 2/3. In the same way as a sphere, you'll probably remember, the surface area of that is proportional to pi r squared. So here we're just squaring the radius, which is proportional to a to the power of 1/3. So already, just by imagining how the strong force might interact, we have 2 terms, the volume term and the surface term. Next we look at the biggest contribution to the energy, the next biggest contribution to the energy in the list, and that's the electrostatic repulsion. Luckily, our laws of classical electromagnetism give us a really neat way of working out the energy that's stored in a particular arrangement of charges. And anyone who, like me, did undergraduate physics will remember spending many, many happy hours calculating the arrangements of different charges that produce such and such an energy for spheres, cylinders, and in all kinds of different coordinates. If you approximate the nucleus as a sphere, then, you can work out a nice formula that's proportional to the square of the total number of charges, z squared. That makes sense because every proton is interacting with every other one. Remember, the electromagnetic force is not limited by distances at all. So there are z times z interactions. And the length scale for these interactions, well, we know that the average distance between these is probably going to be on the scale of the radius of the nucleus, which is a to the power of 1/3. And this of course makes sense again. If you have a very small nucleus like helium, the 2 protons are very close to each other, the interactions will be inversely proportional to the radius, and the radius is going to be very, very small. Whereas if you have a very large nucleus like uranium, the protons will be on average further apart, and so on average the interaction energy for that will be lower. But of course, compensating, there are far more protons in uranium than there are in helium. So we know now that the electrostatic energy is proportional to z squared divided by a to the power of 1/3, and you can work out the coefficient if you like from nice old classical electrodynamics. So those are the 3 biggest contributions, but there are 2 more terms that are important and a little more difficult to explain. Now these are essentially quantum mechanical corrections to the classical formula that's been worked out so far. Now we haven't covered quantum mechanics in depth yet, and we will eventually, I promise, but I'll try to explain quickly anyhow. So the first of these 2 extra terms is called the asymmetry term, and this basically acts to make sure that nuclei don't have too many more protons than neutrons. Because there's a pretty obvious question that may have occurred to you by now. Protons repel each other via the electrostatic force, right? And neutrons just attract via the strong force, but there's no electrostatic force that is causing them to repel each other. So why isn't it always stable to add more neutrons? After all, it seems like the neutrons are just acting like the glue in this situation. They don't add to the repulsion, and in fact they increase the attraction, so why not just add more neutrons and always get a more stable nucleus? And of course, wouldn't the most stable nucleus possible be just a huge clump of neutrons? If neutrons are the glue, why isn't the world just made up of balls of glue, and hence very boring? Well, a free neutron, just on its own, without any binding, has a half-life of around 15 minutes. That means that if you had a batch of free neutrons just floating around somewhere, half of them would decay before you'd even finished your episode of The Simpsons. So neutrons decay pretty rapidly into protons, electrons, antineutrinos, and they usually can't travel very far before they do that. So naively, you might think this explains why we don't see clumps of neutrons forming very often. But on closer inspection, this is no answer at all. After all, the neutron is stable inside the nucleus. Whatever the strong force does, being bound seems to prevent the neutrons from decaying. So why wouldn't a clump of neutrons be stable? And why wouldn't adding more neutrons make the nucleus more stable? It turns out that both questions can be answered due to properties of the strong force and quantum mechanics. There's one really subtle point here about how neutrons and protons bind together, which owes to something called isospin. Without getting into it too much here, it's possible for a proton and a neutron to bind together slightly more tightly than 2 neutrons or 2 protons. So the strong force turns out to be just strong enough to keep a proton-neutron pair together, but 2 protons or 2 neutrons together are unstable, which is why we don't see any nuclei like that. We can see deuterium where we have a hydrogen and a hydrogen nucleus with an extra neutron, so that's a proton-neutron pair. We can see that forming in nature, but we can't see two protons or two neutrons for very long. It's unstable. And by one of those quirks of physics that really start to pile up when you go hunting for them, it's actually only a very small difference in energy, around 0.1 megaelectron-volts. That's about a fifth of the mass of an electron in terms of energy, so it's very small, really, on the scales we're talking about. And this is the difference between a universe with stable proton-proton pairs and stable neutron-neutron pairs. So if the strong force was just that teensy bit stronger, or didn't care so much about spin alignment, they would be stable. Now I don't know what a universe would look like if that was the case, maybe not that different. But I do imagine that it would be very different in all kinds of ways. Chemistry as we know it might look very different. And of course if chemistry is different, if there are these strange diprotons and dineutrons rather than our old familiar hydrogen atoms and things that can interact nicely with each other, well, who's to say that life could even exist in such a universe? So, it's yet another thing to either be thankful for, or comment, wow, this puddle fits me rather well, in Douglas Adams fashion, depending on your perspective. The other thing to keep in mind is, when trying to figure out why there's an asymmetry term, and why there aren't loads of neutrons clumping into the nucleus, is quantum mechanical in nature. So, there's something called the Pauli exclusion principle, and this tells us that no two fermions can be in the same quantum state. Now this means that no two protons or no two neutrons can have the same momentum, spin, and so on. And the reason that this is important for the nucleus is that only so many quantum states are available in the nucleus. And because they can be filled up by neutrons and protons, when you add more neutrons to the nucleus, you're filling up the available states for neutrons. Now this all arises because of what quantum mechanics actually means. Quantum is not just a fancy word for selling razor blades. It means the smallest possible unit of something. So the revelation of quantum mechanics is realizing that on a small enough scale, there are smallest possible units of energy. There are smallest possible units of momentum. The world isn't continuous, it doesn't flow. It's more like integers, 1, 2, 3, 4, than the real numbers where you can have 1.1 or 1.11789 or any value you like. Instead, it's discretized. There are specific values that you can have. And so this means that in the nucleus there are specific states that can be occupied by neutrons and protons. The lowest energy states, with the lowest momentum and hence the lowest energy, fill up first. But if you keep adding neutrons, eventually they'll be forced to be in higher and higher energy states because of this Pauli exclusion principle. They simply can't be in these low momentum states anymore. All the lower states are full. So you need more energy to have this arrangement. Now, this is where the asymmetry term really comes from. It's proportional to the difference between neutrons and protons squared. So it essentially tells you that there's an energy penalty for stacking up too many protons or neutrons. Now, there's competition between the asymmetry term and the electrostatic term. Protons repel each other, so it's good for the nucleus to have fewer protons than neutrons. But if you keep stacking up those neutrons to get a stable nucleus with respect to this electrostatic repulsion, then you can see that you're actually forcing these neutrons into higher and higher energy levels in the nucleus. And that means there's an energy penalty for stacking up too many neutrons due to this Pauli exclusion. So you can't just make things more and more stable by adding endless neutrons. Which is good, because again, that would totally change chemistry and all of the atoms and elements that we know around us if we did that. It turns out that you can work out, based on the ratio of these terms, the ideal ratio for neutrons and protons. So stable nuclei tend to have slightly more neutrons than protons. As an example, one of the most stable nuclei you can get is iron 56. That has 26 protons and 30 neutrons. So you can see that it benefits from a few more neutrons than protons, but you can't just make it stable by adding loads and loads of neutrons in, because of the stacking up of these energy levels would mean that those neutrons would have to be very high in energy. So finally, the final term in the semi-empirical mass formula is the pairing term. This one is also a quantum mechanical term, but it's essentially due to the fact that we've explained before. The nucleons are stacking up in their energy levels. Now, their spins can be up or down. So for every energy level, you have two spin levels, up or down, associated with that same energy. Remember, the Pauli exclusion refers to quantum states. So that's not just saying that they can't be in the same place at the same time. They can't be in the same place with the same spin at the same time, so to speak. So for every energy level, you have an up and a down spin level. This means that if you have an even number of neutrons, you can completely fill up the energy levels. After all, you can have an up-down spin pair, and that energy level will be totally full. But if you have an odd number, the top one has to be half full, and therefore you have a slightly higher energy penalty for stacking up neutrons and protons in a way that results in an odd number. The pairing term essentially accounts for this and penalises the nucleus for adding a neutron or proton that bumps you up one into a higher energy level. And this essentially captures all of the dominant contributions to the energy of a nucleus. You're competing between those terms like the liquid drop model, the volume and surface term, for the nucleons that attract each other by the strong force. And this just takes into account the interactions between neighbouring nucleons under the strong force. Then we have to take into account the electrical repulsion of the protons. Then we take into account quantum mechanical effects due to Pauli exclusion, the energy levels stacking up in the nucleus of the protons and neutrons, and finally the spins. And with that semi-empirical mass formula, you can calculate an awful lot about nuclei. You can figure out a pretty decent pattern for which nuclei should be stable and how they'll want to decay just based on their binding energy. So this kind of thing was used to predict which nuclei would be in this valley of stability before they were even discovered. You know how much energy nuclear reactions will release, and that's pretty important if, say, you want to build an atomic bomb or you want to get a fusion power plant working. When you're thinking about a new nucleus then, it's probably the first thing you want to evaluate and compare. And you can plot it as a function of A and Z, the number of protons and neutrons. There's a pretty good plot on Wikipedia. And you find that the nuclei with the higher binding energy tend to be the most stable and common ones out there for their particular elements. So plotting that formula really gives you a sense of the light nuclei that can release energy by fusing together, and the heavy nuclei that can release energy by splitting apart. So it's a model. It's not complete. There are things that it can't explain, weird patches of stability, nuclei that are sometimes referred to as magic numbers that are extra stable and require more in-depth understanding of a nuclear shell model and the energy levels in the nucleus itself. But in 1935, this was the best theory that anyone had. In the last episode of this saga, we talked to you about Rutherford's discovery of the nucleus, how the general public gradually realised that this new field of study wasn't just going to be on some kind of esoteric pursuit for physicists with insatiable curiosity and rather too much time on their hands, but that it instead had the potential for technological applications that would change the world forever. And this could not have been more clear to the powers that be by the time Carl Friedrich von Weizsäcker came up with the semi-empirical mass formula. Just 4 years later, the pioneering work of Lise Meitner and Otto Hahn led to the discovery that you could make nuclei of uranium split apart if you bombarded them with an additional neutron. Weizsäcker, and by his reckoning hundreds of other physicists, instantly realised what this would mean. There would be potential for a chain reaction, with each fission triggering multiple additional nuclei to split apart. And who knew where this chain reaction would end? The result could be a sudden, massive release of energy. A nuclear explosion. During the Second World War, Weizsäcker, who came up with the semi-empirical mass formula, was sucked into the atomic bomb project. Initially working on more peaceful applications for nuclear energy, by 1940 he reported to the army that energy production from refined uranium was possible. By 1942, this had become decidedly more concrete. He filed a patent on process to generate energy and neutrons by an explosion, e.g. a bomb. It's hard to say how dangerous the Nazi bomb project was. Undoubtedly, Heisenberg and Weizsäcker worked on it. Historians will forever debate how far they got and how enthusiastically they pursued their goal. When Weizsäcker's lab was raided by American soldiers in 1944, they found no evidence of major progress towards a workable nuclear bomb. After the war, several of the physicists involved said that they had pursued it half-heartedly, hoping that the project would fail, for fear of what the Nazis would do with such a bomb. It seems that, towards the end of the war, as the Red Army turned the tide on the Eastern Front, all the resources had to be devoted to the war effort and weapons that worked, rather than weapons that might work. But if things had gone differently, who knows what might have happened. Weizsäcker made some mixed statements about this himself. In 1945, immediately after the news that the Americans had the bomb and had dropped it on Hiroshima, Weizsäcker was detained in Cambridge, and he was secretly recorded as saying, "I believe that the reason we didn't do it was because all the physicists didn't want to do it on principle. If we had wanted Germany to win the war, we would have succeeded." This then was the reaction immediately after the war. But things weren't always this unambiguous. Other historians have suggested that this was concocting an alternative version of history, one that, nevertheless, Heisenberg and Weizsäcker had to persuade themselves to believe. Historian William Sweet referred to it as, quote, a thin and repugnant effort at rationalisation, and Weizsäcker's statements later on in his life were mixed. For example, he admitted in 1957, quote, we wanted to know if chain reactions were possible. No matter what we would end up doing with our knowledge, we wanted to know. He said that they were saved by grace from the temptation to make the bomb. This was the strange world that nuclear physicists found themselves in the 1930s and 1940s. Before, they had been intellectual leaders. Respected academics, yes, but hardly figures of pivotal importance in geopolitics. As soon as it was considered possible to build a nuclear bomb and people began to get their heads around what it would mean, though, the information, knowledge and understanding contained within the brains of these physicists became a dangerous, historically pivotal thing to possess. As is the case with many physicists who worked on nuclear weapons, Weizsäcker, in some senses, seemed to spend the rest of his life trying to make the world a better place. He devoted ever more time to studies of philosophy and politics. In an episode on Stalin and the Scientists, we described how Sakharov, the brilliant Soviet physicist who was pivotal in their bomb project, defected from the USSR at great personal risk, and eventually won the Nobel Peace Prize for activism in favour of peace and against nuclear risks. Weizsäcker spent his later life as much in philosophy as physics, writing passionately about the dangers of nuclear war, arguing that West Germany should be stripped of its nuclear weapons. He formulated a plan for a world government as part of the one world or none school of thinking. Nuclear weapons and the newfound capacity of humanity to destroy itself in struggles between great powers must therefore mean no more great powers, no more European wars and struggles like the First and Second World Wars. He wrote about the inequality between what was then called the First World and Third World countries, and the dangers of environmental destruction and degradation. What motivated so many nuclear physicists to become pacifists, activists, and write in favour of peace? Personal convictions? A desire for atonement? Hoping somehow that Pandora's box could be sealed shut again? Or at any rate that the world could be run by rationality and kindness, rather than tearing itself to shreds in a fit of rage and misunderstanding? I feel that those who helped, however unintentionally, to make the atomic bomb possible, they had a deep understanding of how it feels for things to spiral rapidly out of control. The chain reaction that occurs at the heart of a nuclear bomb is the same chain reaction that scientific discoveries can often create. Innocuous at first, the consequences snowball and butterfly into something quite unintended, something that moves beyond the familiar environments of the lab and academia, and changes the whole world. It's easy to see why, when you're more aware than most about the possibility of unintended consequences of your work to cause great harm, you might want to live in a wiser, more deliberative, and more careful world. Next episode, we'll launch into our series on nuclear fusion, from its early days when Edward Teller dreamed of constructing a super bomb, through all the dreams of harnessing its use for peaceful means. For now, though, I'll leave you with a quote from Carl Friedrich von Weizsäcker, who deduced the semi-empirical mass formula and worked on the Nazi bomb. He said, quote, "The problem is how humans interact with power. In view of the possibility of reason and peace, power is not necessarily the last word. But that is for history to decide." Thanks for listening to this episode of Physical Attraction. All of the usual things apply. Why don't you go and review us on iTunes? Say something nice. It's always nice for me to read them, and it helps people find the show. The best thing you can do to support us, as ever, is tell other people to listen. Our listener base is very, very gradually growing, and someday, I think, if everyone tells another person to listen, then, it will continue to double. It will exponentially grow. We will end up with trillions upon trillions of listeners in all known galaxies, and that would just be a very nice thing, to do from my room. You can get in touch with us on Twitter @PhysicsPod, on Facebook @Physical Attraction. You can go to the website. The contact form is on www.physicspodcast.com. You can find it there. I read all of those because it goes straight to my email. So if you have any questions, comments, concerns, you want to talk about nuclear fusion, you want to talk about the future, you want to talk about the past, let me know, drop me a line, and I will get back in touch with you as soon as I can. Until next time in nuclear fusion then, take care of each other.